That's the problem with social media, by the way. I start this recording right now. Is yeah, there's lots of things in this world to worry about, but you don't usually know they even exist. And now you know all of them exist, and you know they're so horrible, and there's tons of like turtles dying in the ocean because you had one single straw at a 7-Eleven once. That's life. Okay. Goals for today. Here we go. Be able to list and describe the 4 main types of bonding. That's from yesterday. Potential energy curves and their application to covalent bonding and bond length. Yay. Know the basic structure of metals and alloys. Yay. Be able to describe ionic bonding and illustrate. And then my pizza came. And so I there's more. Yep, I got a text. I'm here. I'm like, ... I'm leaving. We'll see. Because if it's like yesterday, we won't make it down the whole list anyway, right? Okay. The goals to be done with chapter 8 no later than Tuesday. And then chapter 9. And we're going to have an 8-9 test together. I always do that. That's not because we're in a hurry. They go very well together. If I gave you just a chapter 9 test, it'd be like 45 seconds long. So, but it's way important. That sounds like, oh, that's useless, but you know, whatever. We're going to be fine. Okay, there is a lot of stuff today, a lot of it. Now, I am not requiring you to do this, but it could help you. If you want to pass the AP test, do things, whenever I say they would help you, you should do them. So on the calendar that most of you don't look at unless you're gone, which is fine, I'm not offended, I have no feelings. So yesterday, you click on yesterday's, has a classroom video, and then I put the corresponding AP class videos on there if you want. So you could watch what I say and then what Alice, whatever says. I don't know. I'm not going to say her last name. Don't remember it. I think it's Alice. Anyway, I did the same thing today, and I didn't do this till this morning. This is annoying. Did any of you type a text and then leave before you hit the most important part? The send, right? I like hired a gal, sent her information. She replied and I replied and never sent it. And then she never showed up. Like 3 months later, I'm like, why'd that girl never come? And then I was thinking about it. And so I was going to send her a different message and I opened it up and all the instructions on what to do to start coaching never were sent. I typed this whole thing up yesterday and then I got here this morning and it was open on my screen, ready to hit create event. You're welcome for me being amazing. It's been a rough 24 hours. Moving on. So today they're here. 2 from yesterday, 4 from today. So, I mean, we're cranking out some major content right now. It all year always feeds into each other. It's like we're making a nice tapestry in each string and eventually they're all going to work out, but whatever. Okay, I will add the class video of this me exactly wasting time right now. That's like mind-blowing. The video of me talking about the video will be on there. Moving on. Okay, I'm excited. Next. Yes. Yesterday, we ended, I believe, on this slide, talking about polar covalent bonds. Will you turn to your partner real quick and describe one thing about a polar covalent bond? Turn to your partner right now and say at least one thing you know about a polar covalent bond. Okay, good, perfect. Your dad should be mad at me. My bad. Yeah. Okay, here we go. My lab partner said one side's positive, one's negative. Everyone agree with that? Yeah. All right. Someone tell me what their lab partner said. Yes, your lab partner said what?
Something that is closer, electron is closer to the.
Okay, the electron's closer to the heavier. I'm going to say the more electronegative instead of heavier. Good? No? Scratching your head? Yes. That wasn't you raising your hand? Who sits like this randomly in life? Like nobody does, but now I know. All right. Polar covalent bonds is when the electron is shared unequally. That's the key. It's covalent, which means it's shared, but it's not equal. That means it's polar, two-sided. All right. So this is what AP absolutely wants to have you know, and I don't remember how far we got, so we'll just click it off. The atom with a higher electronegativity will develop a partial negative charge relative to the other atom. What? Yes, it's the Tom Davidson. All right. Yeah, I'm O. You're right. My wife's hotter. TMI. Okay. So the more electronegative one is the one the electron is more attracted to. So the electron will be closer to it. Next, in a single bond, greater difference electronegativity leads to greater bond dipoles. So let's talk about a dipole. I think it's coming up. Oh, it is. Okay. You can write whatever you want, but you don't have to write this word for word. When two atoms share electrons unequally, a bond dipole results. So dipole, you might need to know, it means two poles. Di means two. Dipoles, like carbon dioxide means CO2. Okay. The dipole moment, or mu, produced by two equal but opposite charges separated by a distance r, is calculated. Mu equals QR, is measured in dBs. You don't need to worry about the math or anything like that. Not even 1 second, but you need to know what a dipole is and a dipole moment, and that's kind of the movement of the electron. They are typically represented with an arrow with a plus sign on that one end to indicate that this end is left positive and the electrons move that way, so it's negative. Okay, that's really all you need to know. A dipole, two poles, that's what we call it, polar. The dipole is the plus sign arrow. No math involved. Don't need to know the unit because you don't have to calculate it. You will just be given the value if you need it. It will just tell you the dipole moment is 2.1 towards oxygen. Is it polar or non-polar? You're like, well, that's pretty big. It's probably polar. Are you all right with that? Okay, so here we go. Once again, in a single bond, greater differences in electronegativity lead to greater bond dipoles. So picture here, I think, we have a very large dipole, meaning the red's showing you where the electron density is. So way red, kind of red, not that red, no red, right? They all have dipoles, but since, well, I'm not going to tell you. You tell your partner, why is this one different than this one? As far as the electrons are almost all here, but here they're more equally shared. How come? All right. I think everyone said it because iodine is not hot. It's less electronegative than fluorine. So the electrons are less attracted to iodine than they are fluorine. Okay, this is a real simple one on the AP test. It would literally be like that picture. It's a explain the difference in polarity. And you'd say iodine is less electronegative than fluorine. And you can say it the other way. Fluorine is more electronegative than iodine. They would not give you full credit. You have to reuse the word electronegative. Sorry. If you use the words, Mr. Burt taught me that fluorine is hotter, you're dead. Okay, here's how they measure, or here would be their values, because it may not be a picture, it could be a chart. And it would say, justify the difference in dipole moments for the above compounds, which is the same, just no picture, it's from a table. Okay with that? The AP test loves tables, it loves drawings, and it loves justification. And it loves math. If you're good at those three things, you're golden. Okay, decent. What? What did I say? 4 things. That's why I didn't pass AP. I wasn't good at math. You know the real reason why I didn't pass the AP test? There was no chance in. I was going to take AP chemistry. I'm dumb. I don't know what you guys are smoking, but I smoked it and I didn't do well. I tried to be smart my sophomore year. I'm like, I'm going to take some honors classes. And then I got really bad grades. And I realized I'm not an honor person. I took dumb classes from then on. All right, this is a weird one here, but all polar bonds have some ionic character. What does ionic character mean? Oh. That's it. Yeah. Okay. Yeah, very much. What were you going to say? That. Okay. Ionic is an exchange of an electron, right? There's not really an exchange here, but they have some part that will be more negative and some part that's more positive. They're moving, but they're not 100% transferred between atoms. Okay, so not a ton here. This is like the cheesiest. What do they mean? Well, who knows? It's just fluff. It says, and the difference between ionic and covalent bonding is not distinct, but rather a continuum. Okay. So it's like in regular chemistry, I teach that the cutoff is 1.7. If the difference is above 1.7, it's ionic. And if it's below, it's covalent. Well, this is saying some that are above will be covalent and some that are below will be ionic. And it's not exactly defined. No, there is no cutoff really, but generally around 1.7. But there's an easier way to know it. And we're going to go there now, so we might as well say it. It's covalent if it has non-metals. It's ionic if there is a metal. This will come up in a second. But that's the real answer. We don't typically do math for an ionic compound. You're like, oh, I don't know. What is the difference in electronegativity? You don't waste your time. You see a metal, which will always lose. Metals don't want to share electrons. So if there's a compound that's not just a piece of metal, it's ionically bound because metals lose. And you can't lose by sharing. You can gain by sharing, but you can't lose by sharing. All right? Unless you're, never mind, I don't have to finish that sentence because that would just confuse people. It would have been funny though. Okay, moving on. We are now to ionic bonding, which we've already talked a lot about, so it shouldn't be anything too new. But ionic bonding, and we just said it, is between a metal and a non-metal. That's your number one indicator that you have an ionic bond. There's really only one time you have an ionic bond, and there's not a metal present. And this will go way back, but if you have NH4 and like Cl, that's an ionic bond. Because you may remember NH4 was called ammonium and was a +1 ion. This is a -1 ion. It's an ionic bond, but there's no metals. Ammonium is the only exception. Everywhere else, if there's a metal, it's ionic. Okay, so here we go. This is AP's words. The difference in electronegativity is not the only factor that we need to consider to designate something as ionic or covalent. Generally, bonds between a metal and a non-metal are ionic, and bonds between two non-metals are covalent. Yeah, I just did it. NH4. It's okay. Examination of the properties of a compound is the best way to characterize the type of bonding. So if it really came down to it, you would just have to investigate. But if you see a metal and a non-metal, 99% chance ionic. Two non-metals, they're probably covalent. Okay, In ionic bonding, we've talked about it when we did like that one slide and I talked for 20 minutes. But in an ionic bond, we form ions. Let me make this a little bigger for a second. So sodium has one valence electron it wants to lose. So it does. All right. It gives it to chlorine because chlorine wants to take it, right? Because chlorine is more electronegative and sodium is very low electronegative. Once sodium loses its electron, it becomes a sodium cation or an Na with a positive charge. Once chlorine took it, it becomes a chloride ion or a Cl with a minus. And then those things are attracted to each other because they are oppositely charged. Now, when a metal becomes an ion, we don't change its name. We say a sodium ion. But I can, for a non-metal, I could just say chloride, and you should know that means the ion. Because we have chlorine, Cl2, chloride, that means the ion that has gained. So like fluoride, all of us probably use some toothpaste today, I hope, and most likely it had fluoride in it. Fluorine, if you brush your teeth with that, that'd be the last time you ever brush your teeth. It would kill you quickly. So fluorine, F2, very reactive. Fluoride, not reactive. Tell your partners why. All right. So hopefully you said something like the electron's already moved. Fluorine is extremely reactive because it wants an electron. Fluoride, what? Already has it and is completely stable. So how does it work with our teeth? Well, it's about half a page in your textbook that you'll never read. It's kind of complicated, but basically it goes into your teeth and replaces oxygen and hydroxide in your enamel. And it makes CaF2, which is almost impossible to separate. So makes your teeth withstand almost everything. Now, it is 10 times more complicated than that. And I have at least 3 kids of dentists in this room, so I'm going to end the debate. 4, 3. Okay, moving on. All right. That is it on metal or ionic bonding. It's not hard, hopefully. Loser, gainer, metal, non-metal, they exchange. We're going to come back to some ionic stuff here in a second, but not bad. Okay, a metallic bond. I'm not going to raise your hands, or not going to make you raise your hands, but some of you have probably gone to church before and don't like, oh, I have. Some of us have probably gone to church before. And if your church is at all like my church, there's usually like at least one mom that has like 15 kids and is overwhelmed. Has anyone seen this before? That's Isaac's mom. Okay. All right. So inside that like church room, everyone's just chilling. And then there's like the 15th kid that decides to just run around. And the mom just says, screw it. Like, you go ahead and run, friend. You do what you want. Because inside that room, first off, all the doors are shut, right? And there's like 30 other moms. And if something did, some moms within 2 feet at any time to scoop him up and make him feel better, right? Does this sound like something you've seen before in your life? Is it the bedsit? It is really accurate. Okay. Now, what does this have to do with metallic bonding? Because, all right, so it's everything. It's the same scenario. Here we go. We have all these moms, and they have all these kids. And you know what? They're overwhelmed. They have the ones that are close that they can hold on to called their core children. I know you're like, this is getting weird. But just go with me. Like the ones they can grab in an emergency. Like, I got these three. But then there's Joey. See the youngest? No, then there's who? Oh, Hiram, duh, Jason's friend. But then there's Hiram on the end, and she just can't grab her. He can't grab it. One's gotten away. That's the valence, right? So you have the core, but then you have the valence that you just can't handle them all. So they just go wherever they feel like. And think about this. At any given point in time, everybody and nobody is responsible for those electrons. It's chemical socialism. They all take care of each other. Okay? When metal bonds with itself, none of the nuclei want the valence electrons. So none of them claim them. They just send them out. You go do you. All right? Another example is a neighborhood with it's a Perry neighborhood where all the grass, it's like one field between all the houses, right? Who's in charge of the play group? Nobody. There's 20 kids out there. They could burn a house down and not a single parent's taking responsibility, right? Like, well, my kid doesn't know what matches even are. Like, whatever, your kid's doing drugs. All right. They're Perry kids. They're built different. But like everyone and no one's responsible at the same time. You with me? The nuclei, the electrons just travel wherever they feel like because they don't belong in a specific place. Now, there is a term for that. It's called that they are delocalized. In metals, we have delocalized electrons. Delocalized electrons means they can move freely. I don't know what that turned out to be, but it's supposed to say freely. What? Okay, so it's not how electricity happens, but it's why metals conduct electricity. Because electrons don't like each other. We've learned that, right? So if I have a wire and it's just jam-packed of all these kids running around after they're like sugar high, and all these electrons are just chilling here, just moving wherever they feel like. If I add a bunch more electrons, all of these are going to say, I'm out of here, because they're offended. And so they go that way. So I made electrons move, and moving electrons is what we call electricity. So metals conduct. This is a really important sentence. Metals conduct because they have delocalized electrons. They're not assigned a specific place. Okay, last analogy. You ready? If we're playing a game of musical chairs, you ever done that? Used to do it in assemblies, but then people get hurt. It's violent. But listen, you're playing a game of musical chairs, but the music never stops. So does the amount of chairs matter? No, because everyone and no one owns a chair at the same time. The electrons, the music never stops. They never have to go home and go to bed or eat dinner. They just move around all they want. You okay with that? All right. Now, when they bond with nonmetals, life's miserable because now the electron, it can't go where it wants. It's where the nonmetal is, and it forms an ionic substance, and the electrons are no longer free to move. So get ready. That means ionic compounds do not do what? They don't conduct electricity. All right. In a covalent bond, they share the pair of electrons between them, and they belong to the two nuclei. So they are not delocalized. So that means nonmetals don't conduct electricity. You okay with that? All right. Yes, sir.
So if you just have like two substances, like physically, one of them would be metallic bond, the other one's just a non-metal and put together, what would happen? Just like, what would happen to the metallic bonding material?
The metals react. They have their electrons stolen from them by the non-metal. You want to see that happen with your very own eyes? Well, okay, little bet. Hold on. Okay. I won. Just kidding.
I told you it's recorded.
No, there's moments in time I don't want your parents to know exist. You have to have what's called plausible deniability. Like, no, I did it. Okay, ready? Well, okay. This is a very like niche part or niche, however you want to say it, part of AP Chem, but it is on there. So you ready? And it doesn't really fit anywhere in the textbooks that we use, but here we are. We need to talk about the structures of metallic solids, which we just did kind of, and alloys. So just a couple minutes here. AP loves drawings and representations. So here we go. Represent a metallic solid. A metallic solid, you would just look at it and it would look like this picture. They use this term all the time. Millie should be here 3 minutes ago. We were having a deep conversation. All right. Never mind. It's pretty deep. Light the world. Okay, but we're going to focus. We're going to focus. So metallic bonding can be represented by an array of positive metal ions, and then surrounded by delocalized valence electrons, and it's a sea of electrons. They use that term in AP and regular chemistry and always. So if you're asked to draw a metal, like the structure, you would just put the positives, whatever, and then you'd have your electrons, and then just like somehow show that they're moving everywhere. Yep, they are delocalized. They are free to move, and whatever. Yeah, for sure. And you would maybe want to say the electrons are free to go wherever they want. It's hard to show. It's just this, and you see how they have the negatives and the squigglies. Like, oh, I'm going to go that way. Like they go wherever they feel like, just like that kid at church. All right, now check. Are you okay with that? Okay, alloys right here. Next pages. Alloys. There's two key words here, vocabulary words, and if you speak English, they're not that hard. An alloy is a mixture. Don't write everything on this slide. Draw the pictures, and that will be good enough. An alloy is a mixture of metallic solid solution composed of two or more elements. Now it's a solid. We're used to solutions being like salt water, but it's just a nice mixture of things in your metal. It can be a solid. Like bronze, the thing that changed the world essentially, is an alloy. All right, examples of alloys include materials such as brass, pewter, phosphor, bronze, amalgam, and steel. What our whole world is built on. All right, complete solutions, solid solution alloys give single solid phase microstructure. Don't stress about that. I should have just deleted that bottom line because that is no longer on the AP test and was very confusing. Okay, there are two types of alloys you'll be held responsible for. They are substitutional alloys. And the word and the definition make sense, or the name and the definition. In substitutional alloys, you have metal nuclear atoms that are around the same size, and you just substitute other ones in. That's it. So in the structure, instead of having 9 reds, you now have 7 and 2 grays. And that can give it better properties or worse properties, depending on the alloys. But we just substitute something in where we normally have the other piece. All right, interstitial alloys form between atoms of different radii, where the smaller atoms fill the interstitial spaces between the larger atoms. Okay, So we use this example at a different time. But when I was a kid, I was in a class and we were talking about making sure we put our priorities in the right space or the right order. Have I said this in this class already? Everything runs together. All right. And so my teacher, he put sand in this jar. Yeah, you're like, okay, been there. All right. And he filled it up to here. And then he put marbles. And there wasn't enough room and the marbles fell over. Sound familiar? I did lose some marbles. But then he said, hey, if you switch your priorities and put the marbles first and the sand second, the sand fills in the gaps and everything fit just fine. Right? So the lesson was put something before something else. Yep, put your family before your fantasy football team. Okay. Yep, I did it all for my family. Okay, so when you have large atoms and then smaller ones, you can get this interstitial where the smaller ones fit in. Okay with that? And those make usually strong alloys. This is how steel is. Steel is one of these. We put carbon in. It's not even another metal. It's carbon and iron, and it makes a new structure that's much stronger and has better properties. Okay, do you need more time on that slide? Okay, I will go get a beverage across the hall then while you do that. And what's his face? Blaine will just upgrade his race car. You all looked at me like this was still on. Mine's only 71.9. Wait, it's really good color on my face in that picture. I have a glow for some reason. Secretly, I did that on purpose. It didn't work out though. All I wanted was for one magical to say, you do have a nice singing voice. It would have changed my life, but you left me hanging. I put it out there, like I went out on the limb and all you did was saw it off. Like, oh, okay.
It was very good.
Yeah, it's too late. Okay. Marriage training, you have to give the compliment before they say, give me the compliment, or it doesn't count. Yes. Okay. I know. Okay. Are we good? So, thumbs up if I can move to the next slide. Okay. I got one. I'm moving. Okay. This next part's confusing. Anyone already confused? For 6 months. Okay. It's not that bad. Chemistry, what I kind of like about it and kind of hate about it, I know that's weird, but it takes something that's not hard and then it makes you think about it in a new way and blows up everything you ever believed in. You're like, really? We're really good. It's the science of making you more confused than when you came in. Now, this isn't awful. It's sort of different. It's just another way to define stuff. So the next little bit is about potential energy curves, bond lengths, and lattice energy. And they're different from each other, but they're all clumped in together. So we're going to represent the relationship between potential energy and distance between atoms based on factors that influence the interaction strength. All right. Yeah, we are. I have a secret goal in this room, and I've never been able to meet it. But one of these days, I can't. It's a secret. But someday, at the end of the when I achieve it, I'm gonna pass out dead. Okay. So the first one, it don't matter. Okay. The essential knowledge here, and don't worry about all these words. It says a graph of potential energy versus the distance between atoms is a useful representation of describing the interactions between atoms. Such graphs illustrate both the equilibrium bond length, meaning the separation between the two atoms at which potential is the lowest, and the bond energy, the energy required to separate the atoms. It's not bad. Here we go. You will see this graph at some point on your exam. It will look something like this. And it has energy versus distance, and then this weird line. Now, there's no such thing as negative energy, right? Like you feel that when you walk in my room, but that's not what we're talking about. A negative energy to us means it's exothermic. You okay with that? It releases versus positive, which is it's endothermic. Okay, ready? So here we go. So the energy is going to release. So I'm going to read all this. I'm going to hopefully make it make sense, and we'll move on. No. Why am I the way I am? Okay, potential. Oh, I'm in a good mood because I slept in. That's why I'm in a better mood than normal. Okay, these are called potential energy curves, also known as potential energy surfaces. I don't know why, but it's okay. The PES is the energy of molecules as a function of the position of their nuclei in R. The energy of a system of two atoms depends on the distance between them. Okay, so if I'm an atom over here and there's another atom by the door, we're not very attracted to each other because we're really far away from each other. As I get closer, the attraction will increase until I get really close, and then the attraction's really strong. And as I get close and that attraction gets really strong, that means the more energy is released as they come together. We watched energy be released, right? But then they get so close that then they're not attracted to each other. Their nuclei are now pushing each other apart. And we cross this line and they are no longer stable because their nuclei are too close and they fly apart. So there's a perfect distance where the attractive forces and the repulsive forces just like hit the right spot. And that is where the bond is formed. And we can measure that distance on this internuclear distance chart. So not much attraction because they're far apart. As they get closer, their attraction increases till they're really, really attracted, but not repulsed yet. But if they get closer, then they push each other apart. Who's even remotely with me right now? What this graph is showing you?
Zoned out at like 5 minutes in class.
You what?
Zoned out 5 minutes.
Zoned out?
And then I tried to like listen it.
Yes, ma'am.
How would I summarize this for notes?
That's a really good question. You would take a picture of this. And then you would listen to me. I don't know how you summarize this in one. Besides, I would definitely say that the bottom of this curve is the most stable arrangement of the two atoms. The bottom of this curve is the most stable arrangement of the two atoms. I'm tired. You know, after you perform, you're just kind of worn out. You come down from that height. All right, now, so far, who's with me? Between two atoms. So this is why I went to this picture, because way over here, the two hydrogens aren't very close. So there's no energy release as they come together. Because, one second, what this graph is measuring, hey, zoner outers, pay attention, please. What the graph is showing you is the energy released as they move towards each other. So if they're far apart, they don't even attract, so they're not going to come together. Then there's still like maybe more attraction, but they're still not going until we get to this part where they're so close, they're like, boom, I'm going to hang out. In this example of me lighting the magnesium on fire, I heated it up enough so that the oxygen and the magnesium could get close enough that then the exchange happened. And it happened fast, and they released a ton of energy. If you close your eyes and you stared at it, you still might have a line in your vision. You can burn it. It's the same as a welding torch. Okay. Then when they get there, that's when they would have released. Or think about this. This is where it would be the hardest to pull them back apart. If this is the hardest it is to pull them apart, then that's the most stable or strongest bond. You okay with that? Okay, so if I was summarizing, I'd say this is the most stable, the bottom of the graph. And then I would say that one more thing is that the distance from the bottom, from here to there, that's your bond length. Whatever the most stable one is, whatever distance that is on the graph, that is literally how far apart those things are. If I get them closer than that, the protons push each other apart. If I move them farther apart, they're less attractive because they're less close. Because guess what law is governing this as well? Coulombs. All right, it's involved in everything. I don't know. Kind of tricky though, right? It is tricky. All right. Okay. Bond length. Bond length, so meaning how far apart the things are, the thing we just saw, is determined by two things. So here we go. It is directly related to the size of the nucleus. Smaller nuclei means that the electrons are closer to the positive charge, which is more force, according to Coulomb's law. Phoebe did not like what I just said. Sorry. I'm in a good mood because I slept in. My bad. Oh boy. Oh man. The longer the bond, the higher you get, I believe. Is that right? If you don't know what I'm talking about, then good for you. BB, I'm worried. Just kidding. How did I do that? They're right next to each other. Okay, here we go. How can I go on? The smaller the nuclei, the shorter the bond length. Get out. Oh boy.